All right, today is Wednesday, 10/28, and these are our notes on acids and bases. And we're going to do this all in one shot. And this really does summarize the acids and base POGL that we did in your packet. So, in the POGL, it talked about Arrhenius's theory. Let me get my marker working here. So, Arrhenius's acid-base theory. He was a Swedish chemist who lived from 1859 to 1927. He understood that aqueous, and remember aqueous means water, solutions of acids and bases conduct electrical current. Therefore, they must, when they break apart, dissolve into ions, those charged particles, in solution. An acid produces H plus or H3O plus ions, and a base produces OH negative ions. So that was his definition. So an acid, he said, was a compound that increases the concentration of the H plus or H3O plus. Really, this is just a water molecule that has a extra hydrogen attached to it. Notice they both have positive charges. Remember, Arrhenius's base was a compound that increases the concentration of OH negative ions. So that was Arrhenius. His definition just had to do with hydrogen and OH, which is called hydroxide. Now, two other guys came along after that, and they were called Bronsted and Lowry. They had a slightly different idea. So they expanded this idea of an Arrhenius acid. With the Arrhenius acids, it only dealt with, as it says, acids and bases that were in that aqueous solution. Bronsted and Lowry expanded the definition to include things that were not dissolved in water. So, for their definition is slightly different. They said the difference between an acid and base is whether protons are, or how the protons are being transferred. So, in this case, protons are transferred. If it's an acid, and if it's a base, protons are accepted. Notice that they're not mentioning any particular type of ion, where Arrhenius mentioned just hydrogen and the hydroxide or OH ions. For Bronsted and Lowry, they really just focused on are protons transferred or are they accepted. So in general, these reactions are what we call an equilibrium system. These systems, these acids and bases are trying to balance out. A Bronsted-Lowry acid is a molecule or ion that is a proton donor. It donates its proton that it has. Oops, let me write that N, more like an N. So an acid is a molecule that's a proton donor. A conjugate base is a species or a substance that remains after the Bronsted-Lowry has given up the proton. This substance can also reaccept the proton because usually it has a negative charge. The stronger the acid, the weaker the conjugate base. If something is a strong acid, it does not want to grab that proton back up. So you're going to have a lot more protons floating around, or hydrogen atoms, hydrogen nucleuses floating around. A Bronsted-Lowry base is a molecule or ion that is nothing more than a proton acceptor. It's going to grab up any protons that are floating around. So looking at our little example here, here's an acid, and here's its conjugate base. You can see the difference between these when we're comparing them is this hydrogen, which we can say is the same as a proton. The hydrogen is present in our acid, and it's absent in our base. And because it's a proton, it has a positive charge. So once we get rid of that, so it's gone, it leaves a negative charge because our charges are no longer balanced. Remember what we said causes a charge is the amount of protons versus the amount of electrons. Let's take a look at the other conjugate base pair. So the other way you can tell an acid versus a base is you can look at the two, and the one that has more hydrogens is going to be your acid, and the one that has less hydrogens. You notice this one doesn't have a negative charge, but it has less hydrogens, so this is going to be your base, or fewer H, I should say. Okay? Now, you can cross off Lewis acids and bases from your notes. We're not going to talk about Lewis acids and bases. And you can also cross it out here in the table. So if you're going to summarize this in as little words as possible, the difference between Arrhenius and Bronsted-Lowry acids and bases, Arrhenius said to be an acid, you're going to have hydrogen. To be a base, you have to have OH negative. Bronsted-Lowry said no. To be an acid, you just have something that will donate a proton. To be a base, you just have something that will, it can be any proton acceptor. So in the second one, we really look at the charges, and we look at whether it's gaining a proton or losing a proton. All right, let's talk about the properties of acids. Acids have a sour taste. Just saying that, you now know that if you're a lemon would have an acid pH, it's very sour. Although, of course, you never want to taste anything in a lab. Now, acids are also what we call corrosive, which means they can destroy body tissue and clothing. People tend to think acids are stronger than bases, but that's not true at all. If you have a strong acid and you have a strong base, they can be equally as harmful. A polyprotic acid just means that it can donate more than one proton. So diprotic would be something like H2PO4. Triprotic would be, or that'd be negative. Triprotic would be H3PO4. Just depends on how many hydrogens it could possibly donate. A strong acid ionizes completely in aqueous solution, making it a strong electrolyte. So the example here, when this is dissolved in water, it's going to break apart completely with lots and lots of ions. A weak acid is basically a weak electrolyte. You can cross off this part right here also, that you won't be doing that. So you want your example for a weak acid, but you don't need to know about the increasing strength. On to the next slide. So bases. Bases have a bitter taste. So what comes to mind is baking chocolate. The baking chocolate that you use to maybe make fudge, you have to add sugar to it for it to taste good. If you ever by accident bite into that stuff, it is very bitter tasting, and that definitely has a more basic pH. Again, bases can be just as caustic or can burn just as badly as an acid. If it's a strong base, it's going to do a lot of damage. Dilute aqueous solutions of bases feel slippery. So again, thinking of something that you probably use every day, soap. Soap has a slippery feel. It is basic. It has a basic pH. A strong base, again, will ionize completely, also making it a strong electrolyte. And it just depends on the extent to which it dissociates, which means separates, and adds negatively charged particles to the solution. A weak base, of course, is going to be a weak electrolyte because there aren't that many ions. We talked about this one in the POGL we did yesterday. We said amphoteric. Whoops, got to spell it right. Is any species that can be either acid or base. And I said what helps me remember that is amphibian. An amphibian can be on water or land. Amphoteric can be either an acid or a base. So zooming in into our example here, water. It can give off a proton, or it can, and then it would leave this part as our acid, and this part is our base. So it can be considered either an acid or a base, depending on what we're looking at. So pH. Don't speak French, so I'll probably mess up the pronunciation of this, but the French words pour avoir hydrogène means hydrogen power. And this measures the acidity or the basicity of a solution, and it's a scale of 0 to 14. So, and we'll look at the scales in just a second, but so it can be calculated if you have molarity for a really strong acid or base. You're not going to need to calculate anything like this for your test, but you need to be aware of where this pH number comes from. So it's the negative log. It's important that we remember that this is a negative log of the concentration of the acid, or the negative log of the concentration of the base. So what this looks like in a formula is if I'm going to have negative log. Whoops, let me write that word so it actually looks like log. There we go. Log, and this is going to be your exponent. So 10 would be an example. And it's going to be, in this case, the hydrogen concentration, 8,3O+. So there's my ion for an acid. Well, this number here is going to be equal to the pH. And it's always going to be a negative number. Let me show you an example of this. I think it works a lot better. So if my hydrogen concentration or my acid concentration is equal to 1.0 times 10 to the negative 4, remember it's a negative log, so I have to have this negative sign. If I have two negatives, that turns the number into a positive. So when the two negatives come together, this will equal a pH of 4.0. Whatever number the exponent is, I'm going to change it from a negative to a positive, and that will be my pH. So here's another example. Let's say that I have an OH concentration. Let me just zoom in over here. I have an OH concentration that's equal to 1.0 times 10 to the negative 12. If the concentration is that, all I do is I put a negative side in front of this, which is going to make my negative exponent a positive one, and my pH will be equal to 12. So whatever that is, we're just going to turn it into a positive number, and that is going to be your pH. All right, this part here, we have one little blank to fill in. Unless you're given something called a dissociation constant, the pH has to be determined experimentally. You can't just, for a weak acid and a weak base, you can't calculate it. You've got to actually measure it when you're doing an experiment. The last part is pH. So when we're looking at pH, we're looking at the concentration of hydrogen ions and OH ions. We're just going to focus on kind of an Arrhenius definition here. So if I'm at a pH of 0, my exponent is 0, and nearly all of the substance has turned into hydrogen ions, so that's going to give you a pH of 0, which would be super, super strong. As our pH goes up, I have fewer and fewer and fewer and fewer, and let me change colors here. There we go. I have, as my pH goes up, so now I have a pH of 4. I have a pH of 7. You can see that my number of hydrogen ions is getting lower and lower and lower and lower and lower until I reach 14, when I have none. I have 0 of the hydrogen ions. Now let's take a look at the OH. So when I have a pH of 0, I have no OH ions. As I go up, I'm getting more and more and more and more and more OH ions. As one rises, the other one falls. Now, I'm going to zoom in on this one spot right here at 7. At a pH of 7, I have equal amounts of hydrogen ions and OH ions. That's why the pH of 7 is neutral. Looking at our chart right over here, you can see substances like battery acid. It's about as low a pH as you can get. So low pHs, oops, let me change colors, means acid. So lower than 7. I'm going to draw a line right here. So it's less than 7 is an acid. Greater than 7 is a base. So these would have a high pH number. pH meter is just what you're going to use because they're such great electrolytes, you can use a pH meter to measure the voltage between the two electrodes. So the higher the concentration of your ions, the more voltage is going to go through. Acid-base indicators are just compounds whose colors change, and you saw examples of that in the POGL, the acid-base one, where you could see that the litmus paper would turn red or blue depending on whether something was an acid or base. And that's the end of the notes. Dun, dun, dun. What we did in class after this is you did a FAT interactive. It's the last page of your packet, and completed that activity.